We could start the second session of the day, and today we're going to have 3 more speakers for the session. The first of which is Lina Necib from MIT, talking about dark matter with stars. Take it away.
Awesome. So first of all, thank you so much for the amazing organization of this conference and of the workshop as a whole. This has been an amazing month, and I guess every good thing has to end. We have to go back to our real lives. But before that, I'd like to take this chance to kind of give a little bit more of an overview of zooming in at the Milky Way, of what is the amount of information that we can get out of data-driven models and data-driven methods in the Milky Way itself. So basically, my group really focuses on mapping out the dark matter in the Milky Way, and we have multiple reasons for it. One is because for larger scales, lambda CDM does pretty well. It's at smaller scales that things kind of get a little bit funny, so it's a good place to look. From a more practical point of view, there has been this revolution in data that we have now, especially with Gaia and soon with Rubin and so many others, that it's kind of, this is the opportunity for us to really, really study the Milky Way and study dark matter and figure out what it can tell us. So basically, I look at the mapping out the dark matter in 4 different spots around the galaxy. So in the solar neighborhood, dwarf galaxies at the galactic center, and in stellar streams. And there are a lot of different projects about all of these. And since this is the 3rd talk I'm giving as part of this workshop, I'm going to talk about something I haven't talked about before. So we're going to focus a little bit more on the dwarf galaxies in the galactic center. But I will shortly summarize the streams and the solar neighborhood. So this is just a reminder of the discussion that we had in the review talk. This was like the week before the workshop started, and it's recorded. And I put all the references in case you're interested. And I just want to kind of briefly touch on these 3 topics just to kind of fill everybody in. So for this first thing here, what I discussed was how we can use simulations to train a neural network to distinguish accreted stars, or what I like to call immigrant stars, stars that are from somewhere else, just like me, and stars that are born in the Milky Way. And you might wonder, why is that interesting? Well, these immigrant stars really tell you about the merger history of the Milky Way. And in work that I did with collaborators back in 2019 and 2020, we actually showed that these accreted stars can tell us about the velocity distribution of dark matter. So basically, if we get the kinematics right of these stars, we can actually try to extrapolate how fast dark matter is going, and that can feed into our studies of understanding the nature of dark matter, that can feed into our studies of how to figure out how we can actually detect dark matter. So that can be found here. And this is a completely supervised machine learning technique. While here, what we did was using Gaia EDR3 and build a clustering algorithm that takes into account for the first time errors, measurement errors, which are really annoying, but something very important that we need to deal with, to look at stellar substructure in the solar neighborhood. And again, we're doing this just so we can understand the merger history and how our galaxy formed, and what are the imprints of these different mergers in the local neighborhood now that we have so much data that we can actually explore. And the last thing that I touched on last time was also how to build in kind of an anomaly detector, so a stream finding algorithm with the Gaia data, looking for, because streams are just anomalous. There are like these beautiful strings that you can see of stars that you wouldn't expect out of a uniform background. And the whole method was how we can actually find this. We posted this paper about a month ago. And we have 110 stream candidates, and we also have a study of the false positivity rate, so we expect about 90 of them to be real. So all cool things for us to check out. But in today's talk, I'm going to be focusing on the amazing work by 2 of my students, Xiaowei Oh and Tree, who is over there, and who gave a talk on Tuesday about something completely different. So I'm going to talk about his other project. And actually, I think having my talk after Risa and Richie's talk this morning is perfect, because they set the stage for the importance of dwarf galaxies and why we really need to understand what's going on there. So let me start by the circular velocity of the Milky Way. So just FYI, this paper is going to be on arXiv tonight. So in a few hours, definitely tune in, and you're going to see the most updated measurements of the circular velocity. Actually, you're going to see it right now. Okay, so let's just go for it. As you all know, prior to the 1970s, we thought that we lived in a galaxy that looks like this, where, as you can see, the sun, which lives at the edge of our galaxy, is rotating a lot slower, or would be, than the center of the galaxy. However, with the work of Rubin and collaborators, we found out that what we have, our galaxy looks a lot more like this. So basically, if you're the sun here, you're rotating pretty much as fast as a star very much near the center. So this is what we call the rotation curves, or the rotation curve problem. And basically, there have been many ways to try to solve why our rotation curves look like this. And the best solution for that is that we live in a big dark matter halo. So without kind of dwelling on why dark matter is there, I think we're all pretty much on board at this point. I can tell you that with new data, and especially with Gaia, we're able to, for the first time, actually have a very detailed kinematic view of our galaxy, which is quite incredible. So Gaia was launched in December 2013 and has actually given us 1.45 or 1.8, depends on how you count, billion stars in terms of proper motions and positions in the sky, in parallaxes, which is quite incredible. The third data release was for June 22, so just a few months ago, and has increased the number of stars for which we have 6D kinematics from 7 million to 33 million stars. So basically we have 1.8 billion stars with 5D and 33 million with 6D. This is incredible. Like, this is by far the biggest kinematic catalog that we have to date. It's just like a kid at a candy store. I mean, who would want more than this? So with such tremendous data, we can make these very silly videos where we can zoom in on a small 19 million subset of stars and kind of forward them and forward their motion over the next 800,000 years and end up with videos that look like this. So it's an insane amount of data. Basically, that's what it is. So what I'm going to try to do with this insane amount of data now, actually a lot of things, but in this particular case, is build an updated circular velocity curve of the Milky Way based on Gaia DR3. So why is that important? Well, now that we have such huge detailed view of, and such high kinematics of the galaxy itself, we can have better measurements that can tell us a lot more about the nature of dark matter at high resolution, right? Like, we have all of this data. Yes, we have some messy astrophysics that we need to deal with, but it can really tell us about dark matter in such different ways. For example, does dark matter have a dissipative component? Because if that's the case, it will have a dark disk. Is the dark disk there? It's a big question. Is dark matter self-interacting? That's also a question that can be addressed by whether or not at the center of our galaxy we have a big core. So there are so many interesting things that we can do with this. The issue is that although Gaia is absolutely amazing, the parallaxes are not good enough for what we need to do. Definitely the faraway ones, especially because if you wanted the rotation curve, you want it to go really, really far out, so you can have like the full distribution, and you really can't do that if you have bad measurements, because that just defeats the purpose. So what we can do here is, and I was excited I could put in data-driven model because that's part of the conference name. We can use a data-driven model to compute distances. So how can we do this? So this was actually originally done in a paper by David Hagedal in 2019 and applied from a paper by Christina Eilers in the same year. And basically, we're going to have spectrophotometric parallaxes, which is a really long word. Basically, what we can do is have a linear model that takes as input the photometry of stars, and in this case, it's actually RGB stars because they're bright enough, and the normalized spectra of these stars, and basically assumes that the astrometric parallax, the parallax that we get out of Gaia, is some linear combination of a lot of these features. And we actually end up with about 7,460 dimensions in this that we're trying to fit. But it works, I promise it works. And once we take out all of the contamination possibly from the halo, etc., we end up with 33,000 stars with pristine distance measurements. Yes, it's much smaller than what Gaia has, but again, good measurements. So let's take a look. What does the rotation curve of the Milky Way look like now? Well, it looks like this. I know, right? Okay, so this is the circular velocity on the y-axis as a function of the radius or the distance from the center of the galaxy. Our numbers, the new numbers here, are these small, very small error bar numbers in red. The ones behind them are the ones from Euler's paper in 2019. And basically, the biggest thing that we did is have more stars, so we kind of like narrowed down the error bars here in the back, okay, at high distances. So this is important because there is actually quite a bit of a sharp decline here. So the rotation curve is falling a lot more than we thought it would. And of course, I mean, if you can stare at it and be like, wait, is that, okay, it is falling, but how bad is that falling? Well, you can try to fit dark matter with a chord Einasto profile or a generalized NFW, where by a generalized NFW, basically we're changing just like that inner slope. And you can see that basically this generalized NFW can't get it to go down fast enough. And we know that this is the dark matter really making a bit of a mess here, because this is at distances higher than 15 to 20 kiloparsec, where the contribution of stars and gas and everything is just like a lot lower. So dark matter is being a little bit funny here, and we finally have enough data and very good data to figure it out. So the two models of the density profiles that we have are the Einasto, that chord profile that I have here in dashed blue, which is the better fit, as well as the generalized NFW, which tries really, really hard to core that distribution, just so it can go down, can go down fast enough here. And just on the background of this density distribution, I just put the NFW just so we can see it visually. So you can see that these new measurements, although we don't really go all the way in, because we can't, they're really telling us that they're about something quite critical in the formation of our galaxy, which is that we have this it really prefers a chord profile. And this has very strong implications, especially, for example, for dark matter. And this is just like, every once in a while, I'm going to throw in my particle physics background in here, and then I'll tell you about after how awesome it is. But basically, if I were to look for a dark matter signal and dark matter annihilating in the center of our galaxy, the fact, if you expect this and you actually find this, your signal will drop by the density squared with an integral, basically orders of magnitude in what you would predict dark matter to do, which is a huge deal. From a little bit more of an astrophysics perspective, why does this matter? Well, there is this amazing plot by Lazar et al. In 2020 that actually has alpha, which is the inner slope of dark matter between 1 to 2% of fire galaxies, actually fire zooming galaxies at different masses. So this, on the y-axis, we have this inner slope. And on the x-axis, we have the stellar mass divided by the halo mass, so mass to light ratio. The Milky Way lives here, bright dwarfs, classical dwarfs, and the ultrafaints. So just how, because of where things are, a cusp would correspond to here, to alpha about -1.5, versus a core that is much, much closer to 0. And what this is telling us is that for very low masses, as we all know, we would not expect to have a core. If this is just dark matter assembly is going to be very much an NFW, just like we learned. However, the open dots here are dark matter only, and the full dots are hydrodynamic simulations. So this is where stellar feedback actually kicks in and starts coring these galaxies without the need of any new beautiful dark matter model. This becomes quite inefficient at high enough masses, so we're not able to actually create these cores. So, for example, where our paper lands is actually telling us, first of all, we want to be cored, so we're in here, and it's also predicting that we have quite a bit of a low mass for the Milky Way. This is only 1.5 10 to the 11, which is at the very radius, which is extremely low. But I think the measurement of the mass of the Milky Way has been dropping in recent papers. Yeah, Risa's making a face. I know. I'll get back to this number, I promise. So this is much lower than expected. Thank you, 5 minutes. Wow. Okay. This is pretty awesome. We'll talk about it later. Okay, the next thing is we need to study the dependence of this on different stellar models, and that will address that number, as well as different more generalized dark matter. So, dwarf galaxies. Now we're looking at this bottom here, and what we want to know is what is the density profile of dwarf galaxies? And especially because now if you end up with a core in dwarf galaxies, then the baryons are not going to save you. They're not going to be able to do it. And in particular, it should be, basically it could be dark matter, or dark matter self-interaction is one of the most popular ones, but ultralight dark matter would do it too. The standard way that for us to do this is called genes analysis, and it makes a lot of assumptions, and it just doesn't work. To be very honest with you, it doesn't work. So in a paper in 2020, we actually were trying to figure out the effect of binaries on density profiles or whatever, and then we built the whole machinery, and we were like, wait, in the best of cases, this doesn't work. So the truth here, this is the density profile as a function of the radius, and the truth here is this dashed black line. And basically, if you only have 20 stars or 100 stars, which is usually what we have for these systems, you end up overshooting. Basically, you just can't get that core. And these are posterior distributions that are just flat. So anyways, this doesn't work. So basically, Tree and an amazing postdoc at MIT, Siddharth Mishra Sharma, actually came up with this idea of how we can use machine learning to fix this. So basically, our goal was to build a method where we can get the inner density profile of dwarfs correctly. The issue is genes analysis just doesn't work. It makes a lot of assumptions. And the solution was to throw graph neural nets. 3 minutes, okay. So basically, what we use is simulation-based inference and GNN to obtain the density profile of dark matter. So this is an awesome slide, actually, by Tree, where I'm going to just give you the intuition behind all of this. So what do we have? We take a simulation of a dwarf galaxy. It has, and we're only looking at 100 stars, which is very generic, what we would measure anyway. The only measurements for dwarf galaxies that we get are the line of sight velocities. We don't have the proper motions for most of them, which is quite unfortunate. So basically, the only information that we have is the position, projected position, and the line of sight velocity. So what we can do is actually form a graph where each node has the distance from the center of the galaxy, as well as the line of sight velocity. And the nodes that connect that graph are basically based on the nearest neighbor. So then every star is connected to the close by stars. Why does this work better than genes analysis? Because stars that are nearby each other are sampling in nearby, like a closer part of the potential. So there is extra information that you wouldn't have otherwise. And indeed, this works. And we can talk about the training set. But basically, we generate a lot of dwarf galaxies in idealized simulations, train it on it, and then form these with normalizing flows, actually get these beautiful corner plots where here I have gamma, this is the inner density profile, and then some scale radius and the density. And basically a cusp is gamma equals 1 right here, and a core is gamma equals 0 right here. And you can see that for the GNN, you can actually distinguish these two, versus for genes analysis, for the exact same system, they end up overlapping, and you really can't tell one from the other. 1 minute, okay. So What we're going to do next is actually apply this to hydrodynamic simulations, and particularly the ones from fire, just because we need to take into account systems that are especially non-spherical. The equilibrium assumption is a little bit harder to deal with, so it's more about the non-sphericity and the anisotropy of the velocity distribution. So just to finish up, mapping out the dark matter in the Milky Way is a really fun game, especially in light of these high-resolution simulations that we have and all the amazing data that we're getting. Please ask questions, and I'm happy to kind of fill in the gaps of all the things I couldn't cover really quickly. Thank you.
Ask questions, please state your name at first. All right, let's start at the front.
Thank you.
Je t'en prie.
Toby Poznański. Thank you. Going back to the Gaia stars, for which you do the spectrophotometric distances.
Yeah.
Question mark dust? Question mark?
Yeah.
Is it not an issue? Dust
extinction?
Dust.
Dust extinction. No, it's not that bad. Just because we are taking the RGB stars, they're really, really bright, and honestly, it's not. Yeah, and actually, maybe I have it in here. Yeah, and we're only looking far away from the galactic center, where the dust is supposed to be a bigger mess in here than further away. So that's why it has not been a problem.
So my second question was about the direction. Do you see a difference in the velocity curve if you look in different directions, or it's consistent? Do you see a structure, or?
Oh, that's a really good question. So basically, we had to cut out a lot of like the halo, what would be potentially halo, and also like the stars that would potentially be disk flare-ups. So that's why it's kind of like the sample is a lot more pristine than it would be to actually detect smaller structure, and it's at about the circular velocity versus like the lower ones and the higher ones would not be there. That's how we kind of tackled that. That's why it's. Yeah, but I have a different project on the escape velocity, and that we can talk about it later. It has the structure. Yeah.
Awesome result and talk, Risa Wexler. I have lots of questions about the analysis and like which data is really driving it, and is it essentially mostly the Gaia data plus this extra photometry? What limits you to the 33,000 stars?
Good point. Yeah.
That's my first question, yeah.
Okay, so yeah, what limits us only there is actually the apogee DR17 spectra. That's what drops us, because we wanted the spectral information. And before, basically when you put in like, you cross-match Gaia, WISE, 2MASS, and apogee DR17, you end up with 120,000. And then when the cuts that we made for the halo, and actually, no, sorry, 43,000, and then we have a few cuts more that drops it down to 33.
How high resolution are those spectra from apogee?
Oh, from apogee? That's a good question. I don't remember, but I think they're pretty high res. Very high res, right? Like, yeah.
And is that an important piece of the analysis?
Yes.
Okay.
Yeah. Yes, that's why. I mean, we are getting 7,000 spectra per star, and they're the ones that actually are setting up like the distances.
Okay, yeah. No, I'm super curious because we will soon have a much larger sample at lower resolution with DESI. Yeah. I mean, we already do, and so I'm curious how that would add to this.
Oh, that's interesting. Yeah.
So we should talk about that.
Yes.
But separately, the result is super interesting. The mass seems crazy low.
It is crazy low.
It seems inconsistent with many other things we know about the dynamics of the dwarf galaxies, for example.
Yes.
So
which is something that has been bothering me, because basically this result kind of gives us a very low mass of the Milky Way. And I had a couple of papers in 2021 about the escape velocity, and they were also driving it down to, but it wasn't as bad as this. It was like 4.6 10 to the 11 or something. And I feel like we're kind of getting into a bit of a split, where the dwarf galaxy and the satellites are kind of like at a high mass, and then a lot of the other local measurements that depend on very different analyses, like between the escape velocity and the circular velocity and everything else, are kind of dropping us to something low. So something has to go, and I think because we're looking at different parts of the actual space, there is something that happens in between that I'm dying to know what it is. So that's something that I'm looking forward to actually talking with you about it, because I want us to actually build a method that extends the entire data all the way through. So yeah, let's definitely talk about it. Yes, hi Martin.
Amazing. Sorry, this is Martin Ray. Amazing. I'm really impressed by the error bars on the rotation curve.
I know.
I wanted to react again on the same point as Risa, actually, on the cut score transition. So you flashed the density profile, but what's the actual core size that you infer from like the best fitting code profile?
Oh, yes. So basically, when we build the, we have the Einasto and the generalized NFW, and the Einasto has one power law in it, alpha, as well as the scale radius and an overall normalization. So these three are the terms that we get.
What I mean is, what's the size where the density profile is actually flat? Because the reason that I'm asking is when we make the plot that you showed as a function of like how cores work as a function of n star divided by m halo.
Oh yeah.
It's at a given scale.
Yes.
So here, so
this one, basically
exactly.
It's 1 to 2% of the virial radius.
Which is like several KPC cores.
Right.
Like 2% of the virial radius. If you assume 10 to the 12, 2% of the virial radius is a 4 KPC core, which is much bigger than what you actually infer here.
So a 4 kiloparsec core actually would kind of get you here, which is 1, 2, 3, 4. So it's kind of consistent actually. Yeah.
No, like from this you would infer that the slope at 4 KPC is basically NFW. It wouldn't be very flat, right? Or like it's.
I think that looks flat to me, but yeah, we can.
I mean, there's some
disagree in there.
Yeah. I just want to say you can have very, very small cores within the center of the dark matter potential.
That's right.
And still end up at 1 or 2% of the virial radius, consistent with the plot and the idea of this bump.
Oh yes, no, that is absolutely true. You can indeed, just because of the 1 to 2% virial radius. I think what I found really interesting about all of this is that the kind of how this slope at very large distances was the one kind of like pulling the whole thing down. But again, basically, we're posting this tonight, and all of these numbers, if anybody wants to do any of their own analysis on these data, so please feel free to do it. But what I want to do is kind of figure out to build more general models for the dark matter that are not they're a lot more flexible than the two that we did just for testing for the first one, and also because actually change and kind of do a whole systematic study of all the stellar models and that dependence, that will kind of give us a much more accurate idea on what's going on, because this was just a single stellar model. And
that would be awesome.
Yeah,
so definitely
we're on it.
Chris Lovell, amazing talk. I just had a quick question on the simulations. So Fire 2 doesn't include AGN feedback at all. How do you think that might affect this kind of cusp core relationship that's measured with these simulations?
Yes, so the AGN feedback, if I remember correctly, is expected to kick in at higher masses. So it makes a lot for over difference, for very, very massive systems I don't think even the Milky Way is probably 10 to the 13 and even higher. That's why we're not really worried about this here. But you're right. I think this kind of is a bit of a complicated view where we land on here. And of course, there are quite a bit of differences between simulations and the Milky Way in general. So I think for me, it's not really about kind of getting it exactly here, but kind of using observation to tell us a little bit more about the stellar feedback, or I'm going to use it to kind of inform our understanding of the simulations, right? Because, the Milky Way is the Milky Way, whether we like it or not, whatever it is giving us, that is the actual truth. Disentangling that from a particle physics model is a little bit tricky, but that's why I think using those very, very small galaxies that don't really have too much of the baryons is kind of really key in understanding if are we producing cores because self-interacting dark matter, or is it just the way it is?
Beautiful, beautiful stuff. I just wanted to comment on the last bit when you say, that because It's just a comment that we have a paper also in which we have tried on hydrosims already, a similar approach.
Yeah.
And we got very, constraining results as well. I think your approach with graph neural networks is better. Okay. So it would be nice, to compare, and also, if we can talk more.
Please point me to the paper.
Yeah.
I really want to see it. And tree is right behind you, so yes, that's awesome. I want to see that.
Round of applause.